we're starting a new session. It's going to be the last session. All good things come to an end eventually, but actually this is going to be a great session that is going to continue along some of the same themes to some degree that you saw in the earlier section, and even possibly expanding it to an even more in-depth, I guess, look at economics. But we're going to start with Adam. Adam is actually a student from math, showing once again the breadth of Joe's intellectual interest, and he actually collaborates very closely also with Raphael. Adam, the floor is yours.
Thank you. And can everyone hear me? Can't tell. Good. Okay. So it's a real pleasure and an honor to be here to celebrate Joe's birthday, and also all of the work that he's done, his contributions, both direct and indirect, seeding and inspiring and supporting other people. I was inspired by some of the other talks to include my own little history slide. It starts a little bit later than some people. So as you saw in some other slides, in 1986, the first TARC was held in Monterey, California. And actually, just a few months later in Toronto, Canada, I was also reaching a milestone of my own. I turned 1. So to be honest, the next few years were a little bit of a blur for me. So I'm going to skip ahead to 2008. And that's the point at which I joined the Cornell math department as a PhD student. And at that time, I had no idea who Joe was. I joined math to do logic, and I actually already had done my master's thesis in modal logic, but I thought, I'm a mathematician, I should do logic. I came to the math department. I started working on large cardinals and forcing and computability theory, and I was getting kind of lost. But one of the nice things about the math department at Cornell, I think still the case, is that they encourage their logic students to pick up a master's in computer science along the way if they can. And that led me to take Joe's reasoning about knowledge class. And that was a turning point for me, because Joe and I got to talking, and pretty soon we were meeting every week, and he suggested I learn some game theory, which I had never looked at before, and I ended up writing my dissertation on logical models of games, meeting weekly with Joe, and Raphael joined us shortly after that and was a regular attendee. And that really just changed my whole trajectory. So I want to just say thank you, Joe. It's because of your guidance, patience, passion, and mentorship that I found a place for myself in academia. Thank you.
Philosophy department.
Yeah, I should mention, I mean, I was coming from a math department. My advisor was in CS. I worked on game theory. Parts of that dissertation were published in econ journals. And now I'm in a philosophy department at Carnegie Mellon. So I think that shows as a testament to the breadth of the work that Joe does and that he encourages in others. Okay, so that's the history slide. I'm going to talk today about logic and game theory, which I thought was appropriate because that goes back to the types of connections I was working on when I was here as a PhD student. And actually, I'm going to pick up on a project that Joe, Raphael, and I did, and there were some sort of seeds of future work that started when I was a grad student, and of course, everyone has many of these seeds that they start and they sort of lie dormant for a while. And I thought this would be a great occasion to go back to one of those, and I found one that I think is actually pretty interesting. So this isn't a published paper. This is kind of work that could be in progress again at some point that I hope to be. So I'm going to talk to you about something that I'm excited about that connects to that previous work that I used to do with Joe and Raphael. So of course the background I probably hardly needed for this audience, but thinking about game theory and very roughly speaking, what a game is just a context where multiple players are making choices in ways that affect other players potentially. So like auctions are examples of games, or choosing which route to take in a traffic flow situation are examples of games. I'm not going to belabor this because I think this is background that's pretty well established in this audience. But when you talk about analyzing games, right, very broadly, you want to analyze them by somehow assuming that players are trying to do the best they can and somehow looking for stable configurations of play. And how you specify the meaning of these notions gives you various different kinds of analysis of games. So on the one hand, we could ask, what does it mean to do the best you can? And this is usually, though of course not always, cashed out as expected utility maximization. So the idea there, of course, is that players have preferences in the form of a utility function. They have beliefs in the form of a probability measure, and they combine those by taking a weighted average, taking the expectation, and they choose an action that maximizes that value. Of course, there are other ways you can make decisions besides expected utility maximization, and I'm going to talk about that. Even more sort of, I don't know, open-ended or controversial maybe is what's a stable configuration of play? And there are many notions of that as well. The most famous, of course, being Nash equilibrium, whose informal gloss would be something like each player is doing the best they can in the sense of expected utility maximization, given correct beliefs about what their opponents are doing. That's sort of epistemic gloss of what a Nash equilibrium is. Right. All of this is informal and broad. I'll formalize the parts of this that I need to give you a sense of what's going on. I'm not going to formalize every single part along the way because it's only a half an hour talk. So, classic, well-known, very famous theorem of John Nash tells us that mixed Nash equilibria, which I'll define in a few slides, always exist, at least under certain conditions like finite players and action sets, for example. And what I want to explore in this talk is generalizing this existence result to notions of, well, I want to call it Nash equilibrium, but where the thing I'm going to change, the way it's going to generalize is that the underlying decision rule is going to be replaced, not necessarily expected utility maximization, but some other decision rules will be sort of slotted in there. So I need to tell you what I mean by that and how the existence result can generalize to these more general notions. And then, in the true spirit of the kind of work that I do and that I've done with Joe and Raphael, I'm going to show you sort of the basics of some logical models that are expressive enough to reason about these kinds of existence results for more general notions of Nash equilibrium. And in particular, the key concept here is going to be one of robustness. And I just want to make a little aside here. One of the reasons that I think Joe and I worked really well together over the years is that we have really similar sort of tastes and sensibility of like what are interesting problems and what are good ways of solving problems, and that just made it really easy for us to work together. But one of the things that I never managed to convince Joe, I mean, I don't want to put words in your mouth, but something I never really managed to convince Joe was sort of really as interesting as I thought it was topological semantics for modal logic. I was in love with that, and I'll let Joe speak for himself, but I don't think I ever convinced Joe to be in love with it as much as I was. But here I have a little chance to involve something kind of topological flavored in a context where I'm going to take another pass at it and try to convince Joe that it's something to fall in love with. So let me now get to the part where I give you some definitions. I'm going to sort of define some things carefully and skip over some things just to give you a taste of what the framework looks like and what we, some examples of what we can do with it. By the way, if you have questions at any point, just interrupt me. That doesn't bother me. Okay, so standard definition of a game, a strategic normal form game, right? It's like one-shot instantaneous game. We've got a set of players that's finite. Each player has a finite action set. So I'm going to work in this simple context. A utility function for each player. I'm going to use these standard notational conventions of sort of dropping player subscripts to refer to profiles of actions or outcomes, and putting the minus subscript to refer. So this refers to the set of actions, the set of profiles of actions of everyone but player I, which is a key thing you want to reason about in games. Player I wants to think about what might all my opponents be doing. So this is very useful notation for that. And now getting to something which is maybe a little bit new. It's not actually new, but a little bit less familiar, the classic stuff. I'm going to define a decision rule for player I with respect to some background game to be a function that looks like this. And the intuition is that it's a function that takes as an input, this is for player I, it takes as an input some beliefs they might have about what their opponents are doing, right? That's what the delta represents. It represents the set of all probability measures on this set, which is everything your opponents might be doing. And it returns some non-empty set of actions, which you should think of as like, these are the correct responses. These are the best responses to these beliefs. So if you've got beliefs mu about what your opponents might be doing, then di mu is telling you the set of di best responses to mu. So example, the decision rule that says you should maximize expected utility can be defined very easily by just on input mu, beliefs mu, just output the set of all actions which in fact maximize the expected utility with respect to mu. Nothing fancy going on here. But I've made it super abstract now. Instead of thinking of a decision rule as necessarily a formula, it really is just this function that says, what do you believe? Well, then I'll tell you what you should do. And there can be ties, that's why it's a set. Of course, there can be ties in expected utility maximization. There might be many actions, each of which give you the highest expected utility. So here's another example, which is going to figure in a little bit later in the talk, maybe I think immediately later. But so the max and min rule, the different kind of decision rule, it says to maximize the worst case outcome among those considered possible. So you have some beliefs mu about what the other players might be doing. You look at all the things that you consider as that other players might be doing with non-zero probability, with positive probability. For each of those things, you look at the lowest utility. You look at the lowest utility you could get for doing the action AI ranging across all of the contexts that you think your opponents might actually do. And that gives you the sort of worst case utility for AI, and you just maximize that. So this is like a pessimistic decision rule. You just maximize the worst case outcome of any action you choose. And then we have a decision rule here too. Again, there can be ties, always returns a non-empty set, etc. So we're all on board with general shape of what a decision rule is. Okay. So now, brief foray into like how this could be connected to logic, and this connects up to a paper that I have with Joe and Raphael. So we'll say that a player is DI rational if she's playing a DI best response to her beliefs. Simple enough. And in this paper that I have with them, what we did was we considered a logical framework which sort of took the standard KD4-5 models of belief and extended it so that it had enough expressive power to reason about players playing actions in games, and more importantly, rationality, players being rational. So you could ask, you have some kind of background model. I haven't given you all the details for this, but you have some kind of background model with a state space, and you can say, at which states is player I rational? At which states omega is player I rational? And again, there's notation here that I'm not explaining fully because it's beside the point, but the idea is the states that player I is rational at, according to decision rule DI, are the states where the action that they're taking at that state is among the actions recommended by their decision rule applied to the beliefs that they have at that state about what their opponents are doing. So there's some bookkeeping you have to do to make sense of this, but you can kind of, I could leave this as an exercise and you could all just, fill in the details on your own if you want. So we had a logical framework for reasoning about rationality in games. And we also provided a sound and complete axiomatization of this sort of class of logics. And I want to just briefly, again, there's even more notation here, and I don't want to dive into the details of it, but I want to just briefly give you a high-level overview that we had. The sort of most interesting new axioms here were those governing, of course, the rationality primitives. So, and they were all of the form, if, I lost my point. Okay, it's too weak. If player I is playing some action AI and they're rational, then what? And this is a big disjunction that says, well, then they must consider various combinations of contexts, of various combinations of actions their opponents are taking possible. Right? So all of this stuff down here is just a bunch of notation to indicate that we had to sort of encode in the logic what follows from player I playing an action and not only playing it, but rationally playing it, some constraints on what they might believe about what their opponents are doing. But because we're working in a logical language that was just sort of 0-1 notions of belief, the probability came into play in defining rationality, but the belief operators were just 0-1 operators. That meant that our axioms could be relatively simple. I mean, the notation is a bit heavy, but the idea is relatively simple. And it also meant that at this level of analysis, at this level of expressivity of the language, the axiomatization was essentially the same for all decision rules. As far as the language was concerned, it couldn't really distinguish different notions of rationality, except in virtue of distinguishing different constraints on what you might be forced to believe. So again, I'm not trying to present this as like, well, now you all know all the details of this. It's meant to be more high level. The key axioms that we introduced were, one was of this form: if you're playing an action and you're rational, then what constraints follow about your beliefs? And one that I didn't put on the slide, which was just, if you're playing an action and you're not rational, then what constraints follow on you about your beliefs? That was what we did in that paper. We did other stuff too, but that was what we did in that paper, which is relevant to this talk. Okay, back to game theory, because I promised you with something about Nash equilibrium. So let's remind ourselves, a mixed action for a player is just a probability measure over player I's actions. So that's classically thought of as something like a randomization. Player is flipping a coin to decide what to do. In the epistemic tradition, it's often more thought about as a component of determining what your opponents believe about what you might do, rather than necessarily a conscious randomization. You'll see that come up in a second. And a Nash equilibrium is what a Nash equilibrium is. It says it's a profile of mixed actions. Everyone's taking a mixed action such that each player is maximizing their personal expected utility with respect to these mixed actions. So you use the mixed actions to give you the expectation of your expected utility of doing various actions that you might do with respect to the actions that everyone else might do. So this isn't, I didn't change anything here. This is the normal definition of Nash equilibrium. But what we can do is we can rewrite it a bit. We can observe. This is a common observation that's actually sort of mind-blowing to students who are taking their first game theory course, because they like to think of a mixed action as a conscious randomization, in which case it feels like you're choosing your randomization very carefully to somehow optimize your outcome. But it turns out that if you look through the definitions, well known, that a mixed action that maximizes expected utility is just one in which all of the pure actions in its support, everything you're doing with positive probability, also maximizes your expected utility. So there was actually no particular reason to mix that way rather than some other way. Personally, it's more like an equilibrium notion. When you mix in this way, other people's beliefs about what you might do cause them to mix in a certain way, etc. The point for us here is that we can rephrase that previous definition of Nash equilibrium by just saying alpha is a Nash equilibrium just in case for each player, and for every action that each player takes with positive probability, that action is a best response to the beliefs they have about their opponents, where of course those beliefs come from their opponent's mixed actions. So here we see quite directly treating the opponent's mixed actions as generating the beliefs for player I about what the opponents might do. Mathematically, it's the same, just a conceptual difference here, but that's how I'm using it. Yeah.
One thing I didn't catch in the previous slides, what's their belief about other people's rationality? Is that common knowledge, rationality?
At this level of analysis, it's sort of not mentioned, but in fact, if you build the epistemic models, it ends up being like a common belief of rationality, because the equilibrium notion requires that each player be doing this and that each player have correct beliefs about what the other players are doing. So if you were to represent it epistemically, it would entail common knowledge of rationality.
Then what's the room for irrationality? The possibility of being irrational.
Well, the models are just general enough to account. It's not like there could be states in the model where players are taking actions which aren't their best responses, and we just don't rule out cases where players are not doing the best response to their various actions. We'll also see sort of more subtle role for it as we go forward in these slides, where we want to distinguish between whether you're playing a best response in a sort of robust way or not. Actually, whether you're not playing a best response in a robust way. But the models are just general enough that we don't sort of hard code into them that everyone is always playing a best response to their beliefs. Okay, so this is just a sort of nice, more succinct way of writing down what a Nash equilibrium is. I even do this in my game theory class because it just helps students remember. I don't have my DI because I'm not introducing different decision rules, but I have a sort of best response function. This is just a nice way of sort of conceptually writing down what's going on. But for our purposes, it gives us a really direct way of generalizing Nash equilibrium to other decision rules, right? We can just replace the expected utility decision rule with some different decision rule. So I've kept the part that says that in a Nash equilibrium, anything you're playing with positive probability should be a best response by your own lights. But I've changed what best response means. It doesn't need to be expected utility maximization now. And I've also kept the part that says that your beliefs are determined by the mixed actions that other players are taking. So it's just a sort of straightforward generalization of Nash equilibrium. Call it a D-Nash equilibrium, where D is a profile of decision rules. As we noted, every finite game admits an expected utility-based Nash equilibrium, but that's not true for all decision rules, as you can probably guess. Here's a very simple toy example of a game that admits no max-and-min Nash equilibrium. And when I say no max-and-min Nash equilibrium, I mean including mixed strategies, because that's how this is defined. And it's just a really simple argument. It goes, suppose we had a mixed profile of actions that was a max-min Nash equilibrium? Well, there are two cases. Either player 2 is playing right with positive probability, or they're not in this mixture. If they're playing right with positive probability, then it's kind of easy to see that for player 1, their worst case scenario is always going to be when player 2 plays right, and therefore player 1 definitely ought to play top, because in the worst case scenario, which is the right hand column, they're better off playing top than playing bottom. But if player 1 if there are unique best responses to play top, then they must be putting all their weight on playing top, because that's how Nash equilibrium works, even in the generalized context. And in that case, you can follow through the game and see that player 2 then ought to be playing left. They shouldn't be putting any weight on right, which is a contradiction. And if we assume that player 2 is not playing right ever, they're definitely playing left, then we can sort of go trace this through and get a similar contradiction. Okay, so perhaps unsurprisingly, if I swap expected utility maximization out, which is kind of nice, it's like continuous, it sort of lends itself to finding fixed points and stuff. If I swap it out for something like maximin, which doesn't seem as good and have these nice properties in some way, we lose our existence result. And I want to point out something here, which is that in the context of maximin, one sort of annoying feature of that is that if you're playing an action that does not maximize the worst case outcome, it may be just on a knife's edge that it doesn't, that after arbitrarily small changes to what you believe about what your opponents are doing, it now has become a best response. And so the point of that is that this is one of the senses in which maximin is not continuous in quotation marks. If we want to make that precise, I'd need some more math. But one of the senses in which it's not continuous is that being irrational might be something that is not stable under very small, arbitrarily small perturbations of your belief. Change your belief in a tiny way, and you go from being irrational to being rational, keeping fixed the action that you were choosing. And somewhat surprising is that this feature is the only obstruction to the existence of a Nash equilibrium for an arbitrary profile of decision rules. So let me make that precise. So to make it precise, I'm going to sort of, so I can define the notion of a local maximum for a function. You can kind of imagine what that would be topologically, right? A function has a local maximum at a point if there's a neighborhood of that point such that everything in that neighborhood is no greater than the value at that point. And then I can call a function everywhere locally maximum if it's locally maximum at every point. And that seems kind of trivial if you're thinking of, like continuous functions from R to R. But our use case here is actually our functions are decision rules, in which case it's not trivial. And so our functions are now functions from probability measures over what your opponents might do to sets of actions. And the idea of being everywhere locally maximum is translates into saying that for all beliefs that you might have about what your opponents are doing, if an action is not a best response to those beliefs, then it remains not a best response for any sufficiently close beliefs. In other words, irrationality is robust. That's what everywhere locally maximum means in this context. And it's really easy to see that expected utility maximization as a decision rule is everywhere locally maximum. Because if you're doing something irrational, it's because the expected utility is strictly less than what you could be getting. And if you change your beliefs by a small enough amount, you just can't raise your expected utility by enough to get it to be maximum. It's because it's a strict inequality and expected utility is a continuous function.
This is a full explanation of our current political life.
Yeah. Any questions? Okay. So the point is that the expected utility decision rule, maximization decision rule, is everywhere locally maximum, which alternatively, with respect to this decision rule, irrationality is robust. And my claim is that property of irrationality being robust is the only condition that's needed to guarantee existence of Nash equilibrium in the general sense. And I'm not going to do the proof of that, but you guys could do the proof of that, because all you really need to do is copy the sort of modern proof, which uses the Kakutani fixed point theorem instead of the Brouwer fixed point theorem, and do the sort of obvious adjustments. And the only sort of new step in the proof is that you need to take the global best response function that's defined in the process of doing that proof, right? And show that that function has a closed graph. And the fact that that function has a closed graph follows pretty directly from all of the decision rules being everywhere locally maximum. So we can just, it's not even like a new hard proof. Like this wouldn't pass muster in the math department where like the point is to have proved something hard. I didn't prove something hard. I just put some things together in a different way and proved something easy. Yeah.
And I understand correctly, there's no particular reason to even have the utilities per se, as long as you have this response function, right?
Yeah, that's right. The expected utility maximization uses a utility function sort of in service to determining the set of best responses. But my notion of, not my notion, the notion I used with Joe and Raphael, and it's appeared in other places, of best response function in general, bypasses all of that. It just takes as input some beliefs, you need beliefs, and it just outputs what are the best choices. Yeah. Okay, so in the, I think, 5 minutes that I have left, I'm going to bring this back to connect to logic a little bit. So on the logical side, if I want to do something similar to what I did with Joe and Raphael and the previous paper, I need some way of talking about robustness, because that was the key feature that I don't just care about whether players are rational or irrational. I really care about whether they're irrational in a robust way, because that's the condition that leads to an existence result for Nash equilibrium. So I need to take something like a logical model of belief, which I have a version of that here with a little bit of extra structure, and I need to include some ability to talk about robustness. So here what I have is a sort of standard economic model for belief of agents, where I've got probability functions which tell me the sort of quantitative beliefs of the different players, and I also have these partitions which we didn't need in our paper, but I am going to need here for a reason that will become clear in a second. But these are also familiar from the econ literature. You can think of this as like the player I's information, like their hard information, and then their beliefs are sort of additional weights that they put on the states that are compatible with their information. It's also maybe not common, but it's not atypical to see in the econ literature a further assumption that says that each player's particular beliefs come from conditioning some common prior on their respective information states. I'm not making that assumption here, but this is compatible with that if you wanted to include that assumption. Okay, so since I only have a couple minutes left, I just want to give you this sort of high-level picture here. As usual, we're going to interpret belief as probability 1. I'm bypassing sort of careful definitions of the language and stuff just to get to the interesting parts. But what we really want to do is define a new robustness modality, or this is what I want to do. You can decide whether you think it's a worthwhile project or not. But what I really want to do is define a robustness modality for each player, which intuitively works by wiggling player I's beliefs at that state and checking whether after that wiggle, or after any such small enough wiggle, if the in-scope formula phi remains true, with the obvious application of applying that to in-scope formula of rationality or irrationality. There's a small technical problem here, which I'm only going to say a couple of words about, which is that these models typically assume like lots of nice conditions about how the beliefs relate to each other, like introspection conditions. And if you wiggle a player's beliefs at a state, you get something which isn't a model anymore, because it fails all the introspection conditions that you set out. But we can fix that problem with this kind of, I find it an elegant maneuver, but again, you can decide what you think of it for yourself. We have to wiggle the player's beliefs not just at omega, but across their entire information set at omega. That's going to preserve all of the introspection conditions, while at the same time, it's sort of like the minimal amount of change we have to do to keep the model being a standard belief model and keep the introspection conditions, but still allow ourselves to perturb beliefs in a sort of minimal way. So I could talk more about that offline if people want, but the basic idea is just you define an I perturbation of a model by just replacing player I's beliefs at every state in their current information set with some new beliefs mu that you got, and we can choose those beliefs to be suitably close to the original beliefs by just taking an open set in this space, which is, of course, this is a finite set, so this is just like a convex subset of Euclidean space. 2 minutes left, so let me really finish up. with this notion, we can define our robustness operator in kind of the way you would think it ought to be defined. So at what states is box I phi true? It's true at those states where there exists an F neighborhood U of the player's actual beliefs at omega. So those states omega where there's a neighborhood of their actual beliefs at omega, such that every belief they might have in that neighborhood, every sufficiently close beliefs, are such that in the updated model where you perturbed the beliefs to be those beliefs, phi is true. So that was a lot of words, but the idea is just if you shake the player's beliefs in a small enough way, it keeps phi true. So it's a kind of interior operator, except it's not taking an interior on topological structure on the state space. It's taking the interior on this kind of orthogonal structure of the set of beliefs over the information cell. And now to wrap up, how would we axiomatize this logic? Here are the key ideas. You see, I predicted that I wouldn't have enough time to do this in detail. As a kind of interior operator, we can expect this to satisfy S4 principles. Since changing beliefs in this way shouldn't affect sort of basic facts about the world, we should expect it to be sort of passed through ontic statements like primitive propositions. And finally, with a little bit of thinking, you can see that if you combine modalities box B, what you actually get is universal quantification over the information cell, which is a modality which is sometimes explicitly included in the language. There's the what you believe and then what you sort of know based on your hard information. We get that knowledge by combining these two, perturbation of belief with subjective belief. And because of that, this combination should satisfy S5 principles. And finally, thinking of rationality, these are the kinds of constraints we had before. If you're playing an action and you're rational, what are the constraints? If you're playing an action and you're not rational, what are the constraints? In this context, we have a richer variety. We have if you're playing an action and you're robustly rational, if you're playing an action and you're rational but not robustly rational, if you're playing an action and you're robustly irrational, and if you're playing an action and you're not rational but not robustly irrational. So we have the normal topological distinction now between interior boundary cases and exterior to deal with. And of course, we can articulate our rationality, our robustness of irrationality constraint. If you're irrational, then you remain irrational under sufficiently small perturbations of belief, which is what we want in the first place. Thank you.